Hello everyone, my name is Yuhui Tu from University of Galway. This work is under the supervision of Dr Noel Harrison and Professor Sean Leen, supported by Science Foundation Ireland and IFORM. Today I want to present my poster on a crystal plasticity inspired deep learning tool to predict structure-property relationship. Here we go. The benefits of deep neural network DNN have been demonstrated in artificial intelligence, such as traffic light signal recognition and defect detection in manufacturing industry. However, application in mechanical engineering seems still empty, probably due to lack of non-destructive experimental big data. Then it comes to me, is it possible to use computational modeling instead? Crystal plasticity finite element CPFE modeling has been widely adopted for the simulation of micromechanical behavior. For example, the tensile stress behavior based on phase and crystallographic texture here. In this way, CPFE models was firstly varied in 5 phase fractions, white region for austenite and black region for martensite for stainless steel. Phase set was then extended to 200 models with unique morphology and crystallographic orientation colored by inverse pole figure. There are 1,000 models running like this, and together they provide the predicted mechanical response, for example the yield strength. The result indicates an increase in tensile strength as the martensite fraction rises. Now we input these structural property relationships into neural network. The developed DNN architecture includes 2 key layers: convolutional layer to condense the characteristics and pooling layer to prevent overfitting. First, I want to show you the stress-strain curve comparison between the DNN and the CPFE work. See here 2 randomly selected models in the same phase set. Then let's check the yield strength of the complete data on the right. As expected, the training group turns out to be more accurate than the validation group because they inform the model. In general, deep learning has achieved 85% accuracy. Finally, let's consider using this deep learning tool in a more challenging situation, that's for realistic microstructure. We may notice the time difference at the stage of preparing the models. Both models predict good fit compared to experiment. However, the computational cost difference is huge. CPFE model runs on a high-performance facility I check and still takes 13 hours, while I use my own laptop to complete the DNN process in just a second. I understand some of the audience may not be the expert in finite element analysis or have no interest in deep learning at all. Not worry, you can still benefit from the tool introduced today. A user-friendly software with interface has been developed to simplify the operation, which can be easily adopted by industrial partners. Let's watch a demo on this TensorFlow-based software. A handy and useful software, isn't it? By the way, it's open access now. You can check the GitHub link here. Within the repository, you can find the full training data for stainless steel and code for abacus running and deep learning optimization. More details on developing your own database are available in the paper on the right. Please cite the paper if you find any code helpful. Again, this research is funded and supported by Science Foundation Ireland and IFORM, which is highly appreciated. Also, thank you for listening.